We will now hear from the speakers of each breakout room to give a short summary of what was discussed. We'll do this in reverse order, starting with the optimist room and the ultimate wish list.
Everyone, I'm Magdalena. So we were the group of dreamers. We identified three main puzzles. And the first one I want to highlight is the formation of binary AGN. And we thought about this, especially in the context of LSST and gravitational waves. So had a lot of discussion about multi-messenger constraints and how they will affect the next generation of simulations. Then we talked about gas reaching the center of the galaxy and how this is still a problem for most simulations to really understand how gas can actually feed the black hole and cause accretion. And related to that, how can we link hundreds of parsec scales to the scale of accretion in the surrounding the black hole? And so then we thought about what do we need to really solve those puzzles. We identified that we would like to have 10 to the 4 solar mass resolution. And I think that is kind of optimistic, but that's what we are looking for. We also were thinking that we probably need dynamic reflection modeling to improve to really understand the evolution of the black holes, especially smaller black holes in our simulations. Something really close to my heart is thinking about subgrid binary AGN accretion and feedback in large cosmological simulations. So we know that post-galaxy merger, we should see the formation of a binary. Then we should think about how binary AGN feedback might differ from single AGN feedback. And if through some independent simulations, we could then come up with subgrid models to model this behavior in larger simulation boxes. Obviously, predictions for gravitational waves. So as pulsar timing arrays are moving towards the are more mainstream now that we have a detection of the gravitational wave background. We might want to think about this as a constraint. So thinking about the gravitational wave background amplitude as one constraint for how black holes evolve through cosmic time. Nothing's complete without magnetic fields. So we want to understand the role of the large scale role of magnetic fields in these simulations, and black hole spin. So through the next decade or so, we might learn more about how supermassive black holes spins are distributed. So we might want to start thinking about this in larger simulations as well. So our proposed ideal model is a model that connects the scales, including mass transport, angular momentum transport, magnetic flux transport, and radiation transport, including a high resolution multi-phase ISM model. So not much. We'll know that we're successful if we can predict the redshift evolution of AGN luminosity, AGN accretion across all halo masses. Again, spin, if we can reproduce spins that we might be able to constrain observationally in the next years, then that will be a measure of success as well. I'm really curious about the scatter and the M sigma relation. So that's something we can reproduce with our simulations. That would be great. Again, gravitational wave background. As you might know, the gravitational wave background that was recently very likely detected is actually a higher amplitude than what we can currently predict using the clustering of black hole binaries from cosmological simulations. So that's something we should be able to reproduce. And then other multi-messenger constraints. So we see AGN binaries in LSST. We might want to think about whether cosmological simulations can produce that. I'm not going to go into caveats because I'll leave that to the other speakers. But that's our wish list. I think it's comprehensive. and I'll move over to discussion, right?
Yeah, great. Thanks, Magda. Any questions for group 4 and the ultimate wish list or challenges from the realist room? Go for it.
I was wondering which observational signatures you were thinking of in terms of spin.
I don't want to answer this,
Or anyone in the room, I don't know.
I guess one thing that I was certainly thinking of is gravitational wave constraints. So thinking more longer term with Lisa, constraining the spin distributions, just like LIGO has done for the stellar mass black holes, and seeing whether we can reproduce that with cosmological boxes. And yeah, Magda, do you want to add to that?
Yeah, and related to that also recoiling black holes, right? Those are related to unevenly distributed spins. So we can predict more about that. I think there are observational signatures.
So I think this idea of using the measurement, the nanograv measurement is really exciting, but I'm wondering what are the biggest uncertainties, or what would it be the most sensitive to, if you know what I'm saying? So in principle, of course, it's sensitive to black hole accretion and feedback and seeding and all of these things, but I wondered, like, does it all come down to the final parsec problem and like whether they actually merge or not? It's not my field, so, and I think you might be
You want to go back to the front.
the right person to answer
the microphone.
Sorry.
Just if you if you stand there, you have the mic.
I'll stand here. Okay, so I agree. There are many uncertainties, right? I'm going to talk a little bit about this on Thursday, so I don't want to give too much away. There are aspects in the final parsec that, such as accretion, circumpounding disk torques, that affect the amplitude, but it's mostly at most an order of magnitude in the amplitude of the background. I think what we really need to do is we need to have a more complete sample of massive black hole binaries, and then dig into the sub-parsec physics that modifies the amplitude from that 0th order estimate. That makes sense.
Yeah, then you could sort of pin down certain pieces of physics.
Yeah, and I think
Isolate them.
you really need to actually do multi-messenger observations of massive black hole binaries to do this, because ultimately the PTAs can only tell us about the amplitude. We're very far away from seeing a turnover or anything that tells us about larger scale environmental effects. But if we have a really good sample of massive black hole binaries from LSST, for instance, then we can actually resolve the population that caused the same signal. So LSST and PTAs have the same or very closely overlapping frequency bands. So we actually see the same binaries we're hearing.
Great. Any other questions? Doesn't look like it. In this case, thanks again to Magda for presenting the results from room 4. Room 3.
Hi. Okay. We discussed how to properly model accretion in numerical simulations, and because, for example, there are different ways we can do that. We can do that with simple models like Bondi accretion, in which we have a few parameters that can be tuned, and this way, for example, we can recover some observation from large scale. But it can happen that even though we can reproduce something correctly, we are not able to reproduce something else. And there are other different ways to model accretion, like subgrid models. And in this way, we can explore different regimes. For example, there are subgrid alpha disks or HADAF, or there are also models that try to put together different accretion regimes. And in this way, it is possible kind of to link and buffer the accretion from resolved scales down to scales that cannot be resolved. And then again, there are other possible approaches like the Lagrangian refinement. And so this is possible to resolve accretion down to smaller and smaller scales. And ideally, it is also possible to go down to smaller scales and reach the horizon scale. And in this way, this would be the way in which we can more properly understand how the accretion proceeds from in a cosmological simulation. But the problem is that we have to put together the feasibility with the proper modeling, and in this way we cannot run, we cannot do statistics and large-scale numerical simulation with refinement up to these small scales. And also, sorry. Okay, another idea is that there is actually no general consensus on what a proper model is, in the sense that we need to have a specific answer in mind in order to decide what is the actual proper model to study accretion. And also, okay, accretion cannot be really studied decoupled from many other processes like dynamics or feedback. Every time we discuss about accretion, we have also to include these different processes. And I think that's it.
Great, thank you. Do you want to stay at the front in case there are any questions for your group? Sorry. Do you want to stay at the front in case there are questions? Okay. Yeah. All righty. Any questions? If not, I have a question. Something that I've always wondered about with this approach of combining simulations on various scales, and that worries me. It's actually a question for the whole room, is what if these simulations are just too different? So say you study something in an idealized galaxy simulation, the flows, and then use that to inform the cosmological zoom-in simulation. What if the inflows in these simulations are actually so different that you cannot extract the lessons from an idealized simulation and extract it to a cosmological simulation? That is not just a question for the speakers. Everybody who might want to comment on that.
That's like true already, isn't it? I mean,
what do you mean it's true already?
You have like a model, I don't know, like the gravitational torque accretion model is valid in a certain regime. And we use it. The Bondi accretion rate model is valid in a certain regime.
Yeah, but should we continue doing that? But like basically how interconnected are the scales is actually the only valid thing. Okay, no, I don't want to say it that extremely. But do we have to follow Daniel's example and just increase the resolution more and more and more in a single simulation because the scales are so strongly coupled that we actually just cannot separate this? Or are there some scales that might decouple from other scales? And if so, where?
We had exactly this discussion in our group, but we did not. We had exactly this discussion in group one, but we did not answer that question. So we think that that is a really key question to think about.
All right.
That's not very helpful.
I guess that was the same.
We in group two confirmed that also had that discussion. We came up with some answer.
All right. Okay. So actually, group two is up next, right? Are there any other questions for group three? Otherwise, this is the perfect segue to group two. All right. So let's thank the speaker again. Go for it.
All right, y'all hear me? Okay, yeah. So I'm here for group two, and we were talking about how do we bridge the scales in sort of a general like simulation sense? What are people doing right now? So first we talked a little bit about what are the problems, like how do we cope with this, the vast range of scales. The ultimate problem is that there is too much of a dynamical range to ever bridge in computation. It would take generations before we could feasibly even build such a computer, if it even gets built. So in the end, since we're not completely resolving the scales from cosmological down to small scale, what's going on with the black hole, or even like particle scale multiphysics going on, microphysics, we have to put in some kind of cheat. There is, in general, some kind of cheat to bridge the scales from large to small, small to large. We talked about two general sorts of approaches. I guess a few. There's like the subgrid, or like top to bottom, bottom to top sort of approaches, where you might take the results of a cosmological simulation and put them in as boundary conditions to a smaller simulation. Use the results of an idealized small simulation to inform a subgrid model for larger simulations. One of our group members, Aaron, actually is going to present tomorrow on some very interesting DRMHD simulations that go up and down. Yeah, should be fun to hear tomorrow. So that was our first discussion of how we can, one approach to how we approach these differences in scales. The other approach we talked about that we think is not very well explored is using machine learning to create an emulator, a subgrid model emulator for what's going on at the small scales. And I think this would be how do we insert a realistic black hole accretion model in a larger simulation, some kind of emulator. And we talked that, yeah, no, it doesn't seem like anyone's doing this kind of training for our particular interests. Like the CAMELS project seems very similar, but it's more geared towards cosmological scales, we thought. So yeah, that's a good research project if anyone wants to do it. Yeah, I think that's mostly what we talked about. We also talked about a little bit like what sort of parameters would need to go into our machine learning models. Like we thought that it probably wouldn't be good enough to just be some isotropic thing. It would need to take some angular dependence, some evolution in time. It would need to obey conservation laws, and we think that we could enforce that in how we build our neural networks. And that it needs to produce something that's observationally realistic. Yeah, and I think that's all we discussed. Well, mostly. Yeah.
Thank you.
If you're going to ask me questions, I just kind of regurgitated what everyone else said, so I might need my group's brilliance to help me.
Yeah, I mean, anyone can answer any question, actually. It doesn't even have to be from the right room. All right. Any questions on that one? Oh,
Yeah.
Yeah, I was wondering for the machine learning, like, I guess the idea is to do a training on like very small scale simulations, but I was wondering in practice, do we have those simulations that we can train the algorithm, you know, like we need like a substantial amount of simulation with different parameters and things like that, right? It's like the camel suits is using like, I don't know, I'm not going to the number of simulation that you run, right? But it's very impressive. Like, do we have that?
Yeah, I think so thousands, that's kind of the order that we think we would need to do if we like even reduce the parameter space of the subgrid model that we want to train. And I think order of thousands is more AGN simulations that have ever been done by anyone. Like combined, we haven't done that many yet. So it'd have to be some kind of coarse grained. I guess in my experience, like with the turbulence community, they do like 2D simulations and 3D, and they try to fold them all together into one machine learning model. Maybe we could do something like that. Don't know.
Well, does anybody else want to comment on that? Not that I can see.
Yeah, I guess I would add one more thing that we didn't really talk about was magnetic fields. As soon as you put magnetic fields in this, like even doing subgrid models with a consistent magnetic field injection is kind of miserable. So,
Definitely.
so yeah, we don't know.
That could be a discussion session on its own, maybe tomorrow. Okay. Oh,
Yeah, there's a question for the room, more like, and I also think I asked this 8 years ago, but I hope the answer changed. Which is that, we have lots of different people actually running many simulations, and like, do we now 8 years later have a better platform for like sharing simulation outputs with each other so that we don't all need access to each other's supercomputers to do comparative analyses? Huh? Okay, do you want to tell us about that? I don't know about it.
So this is a still in development effort that we're trying to get more support for here at CCA, but we have made a start at Flat Hub stands for, maybe it doesn't stand for this, but the idea is that you can not only download simulation data from different simulations, but that there's actually a dictionary so that like you can compare across different simulations, because of course you never know like what's apples and what's oranges in different simulations. So we currently have Illustrious TNG, Simba, Fire, Santa Cruz SAMs. You may be noticing a pattern here. We're working on getting Eagle. And anyway, the idea is that it would provide that. But again, has a long way to go. So I think that's a really great thing to bring up.
thanks, Rachel. Does anybody else want to comment on that? Yeah.
We have been trying to make our simulations public for years, but what we're missing are people who actually can invest that. If you don't have a significant infrastructure and people who can invest time for a single researcher, it's very hard. So this is a real problem. I agree with you, because we're moving towards open science, public data, but then if you ask yourself, can I invest 6 months of my time on that? Most people who are researchers or professors cannot do that. So asking to Rachel, so would you be open to other groups joining this? What type of support there is to make this, a global hub?
Back to Rachel.
So we, the few of us who sort of spearheaded this would love that. What we keep bumping into is exactly the challenge that you're mentioning, and that, the directors of our scientific computing core are like, we do not want to host the world's simulation data. We don't, like, even Flatiron does not have that much disk space. So I really feel this is something the agencies should be supporting, right? Like in the US, NASA and NSF should be supporting this. And there's like, as far as I know, almost zero support for this kind of thing. There's been talk about doing this through MAST at Space Telescope for a long time, but that hasn't really amounted to anything. So the way it currently stands is that we can only host data from sort of people who are here at Flatiron, which is why like the simulations I just mentioned are all sort of from people at Flatiron. But this is something, maybe someone should write a white paper or something for the various agencies, both in the US and elsewhere.
Yeah, and across continents, it's even harder.
Yeah.
I guess I'd say in the US, where the funding is definitely moving toward, like, the popular funding is moving towards AI. So if we market this to the agencies as, we need this data so that we can do AI because our data keeps being thrown away. What if we have this data repository? Maybe then it could get funded out of the AI initiatives.
Great point.
I like that angle.
It's true, right?
Yeah, definitely.
You can't train your AI if the data is not available.
Just saying, like 5 years ago, there was NSF had the National Data Service, NDS. So that had the same idea of hosting, no, not just astro simulations, but all physical sciences, but that kind of died off in 2018. But the idea was there. I don't know if you can kind of rebrand this under the AI training data. Yeah.
Anybody else want to chime in on that? No? Okay, but great discussion. Definitely something to keep in mind here. Very important. All right, so maybe let's move on to the last group, room 1.
So I have to say, a lot of us seem to have converged on the same ideas, so you may hear the same things again. I think one of the things that we talked about most, again, was this idea of trying to develop a set of simulation initial conditions for the accretion disk simulators. So creating some kind of sample of what the observable universe would produce, and we don't currently know what that would look like. And then feeding that into someone's accretion disk simulation, where then we would want various types of energetics, as well as keeping track of both the mass magnetic field and angular momentum fluxes, and training some kind of smarter subgrid model. Machine learning got brought up again in this context, and maybe some kind of stochastic element as well, that would take into account unexplained differences between codes, as well as time variability on scales that one does not currently probe in your simulation. So yeah, again, on these things that have not been explored as much, especially in the Zooms, we talked a lot about the importance of the magnetic field and whether or not it would be necessary really to transport it all the way down, and on what scale would it actually matter. We discussed that if everything is a magnetically arrested disk or a MAD, then we would be lucky that things saturate at a particular value, but we're not sure if this applies at all accretion rates and in every environment, and there may be differences if the initial conditions are a bit different. And then similarly for angular momentum, if you want something like the energetics coming out of some smaller machine learning stochastic subgrid model, spin is a likely ingredient that is going to matter for things like the radiative efficiency and the jet power. And so tracking the angular momentum transports down to small scales becomes interesting, and there hasn't been as much focus on that as opposed to the mass so far. Although we've had lots of interesting talks showing flipping of the angular momentum directions, and maybe probing that more in different kinds of environments and different Eddington rates would be interesting as well. Finally, in the last 5 minutes, we talked about how, although there's been a lot of research in radiation and jets, there hasn't been so much on winds. And the tricky part would be that accretion disk simulations are usually converged within 30 RG, and the winds will probably come from between 30 and 100, and it would simply take longer to converge your simulation up to that point. But overall, it's a good time to start bridging scales, at least in terms of some targeted simulations, and even though we won't be able to ever do the entire problem. All right, I think that's it.
Great, thank you. Any questions or comments? I'll start us off then. So you talked about the magnetically arrested disks, and that one might not always be in that state. So what is the evidence around this, both from observations and from the small scale sims?
Yeah, so observationally, the Event Horizon Telescope images have both of them for M87 and for Sagittarius prefer these stronger saturated magnetic fields over the weak ones. This is coming, strongest evidence comes from either the linear polarization information or the spectra in multi-wavelength. And so, well, this is a sample of 2, and they're also both low Eddington rate. Now, there are reasons why one might expect that other more generic black holes, at least at this low Eddington rate, might also be in the same state. There are fundamental planes. There's, of course, the one between 5 gigahertz and the X-ray. There's actually a more recent one just this past year that is between the millimeter and the X-ray as well. And there, you're more confident that you're actually probing event horizon synchrotron emitting material. And then in the simulations, they tend to form from generic initial conditions, just like a Bondi flow with a vertical magnetic field. In fact, if you want to set up a long simulation that doesn't saturate, you often have to put in some pretty ad hoc loops that will cancel out as they make their way onto the horizon to prevent this from happening.
Okay, thank you. Any more questions, Jake?
Kind of generic question I don't really know the answer to the room, I think, potentially, but also, do we have any idea of the angular momentum content of jets or winds or outflows from black holes? Because, I mean, we can get the angular momentum through in a cosmological simulation, for example, we can get the angular momentum through a kiloparsec or something. And if it was all just being accreted on, angular momentum is conserved. Great, we know what's happening, but what's coming out is changing that. But do we have any constraints on this? Anyone?
Do you mean the angular momentum loss from the jet? Was I understanding?
Yes.
Okay, I'll tell you tomorrow then.
Nice little teaser there. Okay. Anything else? Okay, if not, let's just thank Angelo again for the nice summary.